Everyone, welcome back to another video. Today we are going to discuss another room on TryHackMe, and it's a continuity of the OWASP open source web application security project, and we are going to dive deeper into application design flaws. Previously we discussed IEEE, and now we are going to discuss the number 2, the 4, 5, 6 and 7 ranked vulnerabilities that are being exploited that were exploited mostly in the 2025. So the A02, A03 and A06 and A10 are generally the names given based on the annual year it was exploited the most. And now let's start our room. So there's this nice cool introduction. So this room breaks each 4 of the OWASP top 10 2025 categories. In this room, you will learn about the categories that are related to failures in architecture and system design. You will put the theory into practice by completing and supporting challenges. The following categories are covered in this room. We are going to see security misconfigurations, we are going to see software supply chain failures, and we are going to see cryptographic failures, and we are going to see the insecure design as well. And we do have a practical as well, a hands-on lab to demonstrate these vulnerabilities and its impact in the real life. So let's join this room and let's complete our task number 1. And we are gonna move to task number 2, which is security misconfigurations. So what exactly are security misconfigurations? Security misconfigurations happens when system servers or applications are deployed with unsafe default settings as such, and there are incomplete settings or exposed services. That's primarily what is called a misconfiguration. So these are not really the code bugs, but these are really the mistakes in how the environment, software or network is set up. Some technical guy might be using some incomplete or incompatible services, or it is quite possible that on the accidental basis some default settings or some services are left exposed for the attacker. So in this case, these are the entry points for the attackers, and these are really severe, and it could lead to why it really matters is because even the small configurations can really expose some really sensitive data, and this could enable privilege escalation or give attackers a foothold into the system. Also, the modern applications rely generally on the complex stacks, so cloud services and third-party APIs as well. So a single exposed admin panel or even an open storage bucket, which is used in AWS, or misconfigured permissions can generally compromise up the entire system. And a common example of this is in the year 2017. Back then, Uber exposed an AWS S3 bucket. S3 buckets, you can consider it as generally where the data of the users are stored in the cloud. It was left exposed on the Uber site, and it did have the driver and rider information, and these buckets are generally available to the public. And since it was available to the public, attackers downloaded this data without even needing up the credentials, and it really demonstrated how a development mistake can generally lead to a significant breach. So let's discuss some common patterns of security misconfigurations. These could be some default credentials or weak passwords left unchanged on the web application. It could be some unnecessary services or endpoints exposed to the internet. And the services, for example, if there is an FTP service being opened on the machine, and you don't need as such, but it is being exposed. So it is quite possible that attacker might try to just try default credentials, and even if there are some default credentials set up and they are not changed, then it is a misconfiguration. An anonymous login on the FTP could even allow us to get sensitive files. So that's why it's important to generally configure the passwords and don't use the default credentials. And misconfigured cloud storage or permissions could also lead the attackers to sensitive data, and unrestricted API access is also a common pattern. And generally error messages which are exposed on this system are also the common behaviors which could be used to analyze what the application is doing on the back end. And the outdated software is generally exposed to common vulnerabilities, and it could be exploited by an attacker if some previously known CVE is assigned to that vulnerability. And exposed endpoints without proper controls could also give us the sensitive data. So how to prevent it? So you need to harden up the default configurations, you need to remove the unsafe features or services, you need to enforce strong authentication, least privilege across all the systems, you need to limit your network exposure and segment up the sensitive resources. Only the particular person or the intended person should have access to that resource. And you should keep your software, frameworks and containers up to date with the latest patches, and you should hide your development traces, what you are using on the back end. On the client side, it shouldn't be revealed what versions are you using on the primary tech stack you are using, because that version could be vulnerable, and an attacker could just search up for the vulnerability and exploit it. As such, it is as simple as that. You need to audit the cloud configurations, and you need to see what permissions the services are using. You need to secure endpoints, and you need to prevent automation on these endpoints. So we need to integrate configuration, and as such we are given to navigate to the machine IP. We are given a machine. Okay, so we're gonna start this machine. So it's gonna start up, and for now let's consider what is software supply chain failures. So it is given the AS03 most exploited in the year 2023 as such. So what exactly it is called software supply chain failures. They generally happen when applications rely on components, libraries, services, or models that are compromised, outdated, or improperly verified. And generally these weaknesses are not inherent in our code, but rather it is inherited on the software and tools you depend on. For example, if you are using React to develop your web application, so that React might be using some components as well for its essential working, and these components might be vulnerable. For example, there was a vulnerability called React to Shell, which infected all the servers using React as an application and React as a framework to develop or host their website. So it affected all. So software supply chain failures means such that you are using your code, you are relying on someone else's code and someone else's tools, and these can be used to bypass security. These can be exploited. These can be used to inject malicious code. And why it generally matters that modern applications are generally built from third-party packages and APIs and AI models. So if they are compromised, then their dependency can compromise your entire system, and it could allow the attackers to gain access without even touching your own code, and it is as severe as it is. So a common example of this is the 2021 SolarWinds attack. So Orion compromise SolarWinds Orion compromise showed the danger of supply chain attacks. So basically, the attacker inserted malicious code into a trusted update, and it was coming as a legitimate update. So it was all of the organization using this software just generally trusted it, and it resulted into affecting thousands of organizations that installed it. And this wasn't even a bug in SolarWinds core logic, it was generally a flaw in the software update building, verification, and distribution process. So with the AI, we can observe this when using unverified third-party models, or we can see that when we are trusting some data sets, what hidden behaviors, what hidden backdoors it is being used. So some common patterns of this software supply chain failures is that you are using unverified or unmaintained libraries and dependencies. You are automatically installing updates without even verifying what are they patching up, and it could be generally more relying on the models, on the AI models, giving everything to the AI models. And it could an AI model, if exploited up already, could give you a malicious code, and there could be insecure build pipelines or processes that allow tampering, that could allow a connection back to the attacker. And there could be a common pattern could be to poor license or just not tracking up the components. It could be lack of monitoring for vulnerabilities on the dependencies that rely on your development. And how to protect from the supply chain. You can protect by verifying all third-party components. You should see what libraries are you using in your development, what tech stack dependencies are you using. You need to monitor and patch dependencies regularly. You need to verify your software updates. You need to verify what third parties are you using. You need to verify what are you giving to the LLM. Need to verify what are you giving to the APIs, or what endpoints you are giving as a result. So you need to track and license all the dependencies, and you need to generally verify what are you using in your own code, what are you using from the external third party, because it is quite possible that external third party could be vulnerable to might be using an outdated version, and thus it could be exploited as such. I'm gonna give a view of task 4 as well. It is cryptographic failures. So cryptographic failures happen generally when encryption is used incorrectly, or generally not at all. So basically, encryption is used to keep the data of the user secure. For example, if you are using the password to authenticate into a website, that password must be encrypted and then stored on the database, rather it just stored as a plain text. So this unencrypted sensitive data is a cryptographic failure, and this could be due to weak algorithms such that could be predicted for the particular output, and these could be hard-coded keys. For example, if you are using an algorithm to encode your password and you just expose it on the client side that you are using this algorithm, it is a cryptographic failure that just generally fails up the entire purpose of cryptography. So these flaws can let the attackers access information that should be private. And why it matters is because the web applications rely on cryptography everywhere. You need to protect it includes all from protecting network traffic, securing stored data, and verifying identities and safeguarding secrets. The cryptography is generally used a lot in the modern day web applications. It could include from everything sensitive, from passwords, tokens, or even personal information. It shouldn't be stored as plain text. It should be used with a particular cryptography. It should be encrypted, and it should be using some encryption at the most core level. But if this encryption is not secure and it is predictable, then it fails the cryptography and it fails the purpose of using the encryption, and it leads to cryptographic failures. And how it could lead to cryptographic failures is it could be exploited by using a man-in-the-middle attack, or it could be exploited by brute force attacks, or generally using weak keys, or just simply discovering secrets that were never properly protected as such. So a common pattern of cryptographic failures is using weak algorithms like MD5. MD5 is not secure at all. If your password is using MD5 and someone else gets hold of your password, not the password, but if on the, let's say you visit a web application and the web application was saving the password of the user in its database as an MD5 hash. So if you get hold of, you compromise the entire database and you get the hold of the MD5 hash. Now this MD5 hashing is generally a one-way function. Like if you have a password, then you can just get the hash out of it. But on the most core level, if you just compute the commonly used passwords and then compare its MD5, you can ultimately reverse the process, meaning you can try to iterate over the commonly used passwords and you can generate its MD5, and you can just come out with the original password by comparing every MD5 hash of commonly used password and just seeing if it matches or not. So that's why MD5 hashing is not secure, and similar is the case with the hashing algorithm SHA-1 and ECB mode as well. So hard-coded secrets in the code is also vulnerability. It could be used to generate the secret and thus leading to poor cryptography and poor key rotation, self-signed or invalid TLS certificates, and using AI systems without proper secret handling for model parameters or sensitive inputs. And how to prevent this? You should be using modern algorithms like AES, GCM, and these couple of more valid. You can read it as such, and then use the secure key management services like Azure, AWS, or HashiCorp Vault, and then rotate the secrets and keys regularly. Follow defined crypto periods, like not to rely on a particular algorithm and not to rely on a secret. If anyone gets hold of that secret, then your entire cryptography fails as a result of it. And you need to maintain a complete inventory of certificates, keys, and their owners who have the access to the secrets, who can make changes to the secrets. And you should never ever expose unencrypted secrets or sensitive data on the web application. That basically fails the purpose of using a cryptography, and overall can be exploited. So then we have this insecure design, which is AS06. So this is basically insecure design happens when there is a flawed logic or architecture is built into a system from start. So these flaws generally start from script threat modeling, no design requirements or reviews, or accidental errors. Insecure design means that on the back end, this design is not secure at all. It is allowing the users to do the purposes it is not even intended to do so. But it all leads due to the design practice being used. I will try to explain. For example, if the software generally asks the user to open a file, and if that file is opened, but further, if there is such a design on the code that you could open up even the files of the server as such by exploiting the design, then it's a practice of insecure design. So moreover, with the introduction of AI assistants and with the vibe coding these days, this means there is a predictable pattern that these AI or LLM based models used to write the code, and these are not properly trained to secure the development process, and it gives out a lot of sensitive information. It generally uses an improper design and insecure design. And what I mean by this is they'll either expose up the secrets, or they just tend to use a logic that only just works by hook or by crook, and they don't either care to secure it. For example, if I give you the example of opening up the files, and a particular line of code could be changed as such to open the files on the server if it is not properly sanitized. Another example could be if there is an input field and it is generally allowing all the inputs, then a particular cross-site scripting payload could be injected, or any malicious code could be injected there, which could be run on the server on the backend. A popular example of it is Clubhouse. It's an early designed assumed users would only interact through their mobile app, and they generally don't care. And it was like the Clubhouse relied for the users to only rely on their mobile app, and they should just interact with it. But they exposed the API, and it had no proper authentication. So anyone could just query user data, room information, and even private conversations directly. And when researchers tested it, so the entire design was insecure, and it was exploited up by the attackers. So why it matters is because you can't patch an insecure design. It's built into the workflow logic, but you need to somehow not rely on the AI and try to not give the permissions of the unintended things that would be exploited. And common insecure designs in 2025 is weak business logics like recovery or approval flaws, flawed assumptions about user or model behavior, AI components with unchecked authority or access, and missing guardrails for the LLMs and automations to not to secure it properly, and just not to write the code and make the code functional, but to use a proper secure mechanism for writing that code. And AI generally introduces the design flaws. The system prompt, for example, an AI LLM could be given a prompt injection payload. If it is not properly sanitized, it could be tricked into doing the purposes it is not even intended to do so. And how to design securely is to treat every model as untrusted, use more human code and then AI code, separate system prompts from the user content, and just treat the LLMs securely. Just apply the principle of least privilege escalation, not expose up the APIs, try to secure it as such by not giving the permissions, and continuously monitor for the logic flaws, abuse parts, and if anything is going wrong as such. So now we're going to discuss the labs, and first up we have security configurations lab, and it's being hosted on the 5002 port on this particular IP. So let's see, what do we have? It's a security misconfiguration lab, I guess. So there should be some misconfiguration. Get API request to user winter free. Let's give a get request over here. let's see. Okay, so we are given with John Doe. Let's try if we could just get a log out of it. Any error might be revealing something else. Let's do this. Okay, so we got our flag. It was misconfiguration, so that was pretty clear. And then we have our software change suppliers lab. So it might be having something. The code is outdated and imported and old. Okay, so we are given a task file too. Let's just download it and let's view what it's doing. Let's view the code. Okay, so it's a couple of default modules being imported, and then we have an import from local. I have so many tabs opened up. Okay, so importing from local unverified library, and then we have the app giving a normal post request to API process and process user input using third-party library, missing data parameter, and if data is equals to debug, then it returns us the debug info. So so by the looks of it, this looks like our end goal. Let's see. I've opened up the burp suite, I guess. Yeah, so we gonna get this request. I am gonna send this to repeater. Sorry, not this one. We are gonna see what do we have over here. Okay, so we gonna send a post request to this endpoint. Let's see. I'm gonna send this. We gonna have a request on our burp. Okay, I'm gonna send this to repeater. We're gonna change our request method to post, and then let's see this request on burp. We can see that it's sending a post request with an encoding as such URL encoded, and then we get an error that content type was not JSON. So we are gonna give it application JSON, and let's see what do we get. Okay, so failed to decode the object. Okay, so by the looks of it, as we read in the source code, check for debug mode. If data is equals to debug, then we are going to get some debug logs. So how JSON data is given is we are going to give data, and I'm going to give it a value of debug. So a nice clean input data, and then it's having a value of debug, and then just closing out. So let's send this request. Okay, so we get the debug logs and it has our flag in here. So we gonna get this flag, and I am gonna give this flag. I'm gonna submit this flag, in fact. And then we have cryptographic failures lab. So on 5004 code, let's view it. What are we presented with? Okay, so we have a secret given as such on the encrypted document. Let's see if we have anything on the source code. Okay, we have JavaScript used to decrypt. Let's read it. So my secret key. Okay, so we have the secret key being revealed, and there was one thing more, and the encrypted document too. Okay, and there's encryption ECB and the key size, and nothing else so interesting. Okay, so we can decrypt this using CyberChef. I am gonna give this encrypted document. I'm gonna give this, and let's look what is substring. So it looks like an AES encryption, and it's having long characters, so I guess it's base 64 first, and then we're gonna use AES decrypt. So we are gonna use this key, The key is my secret 16 and it's UTF-8. Mode is ECP and input. There is one more thing. Key size is equals to 180. So there is no such initialization vector. Wait a second. Step unable to decrypt with these parameters hex and raw. Okay, so it's raw. Okay, we were giving just one hex and the other hex as 2. So admin password is 123 and we got our flag 2. So I'm gonna submit this as well. Then we have our last lab in secure design, the port 5005. Let's see what do we have here. So download the mobile app. So if you remember, there was some API discussion over here, so it looks like more an API theme challenged. Okay, so let's see if we got anything. I'm gonna use a GoBuster to brute force the API endpoint on this. And API, let's see what do we have. Then okay, so it's an HTTP. Okay, let's brute force this command.txt. We are looking for an API endpoint over here at this point if it's exposed for the users. Okay, so we found the endpoint which is users and it is here, API users. Let's see what do we have. Okay, so we have this user admin. I'm gonna say to admin. Okay, so let's see if we have another endpoint beside this. I use pic.txt this time. API users, and it's gonna find another endpoint which exists. Look at it. So it's a messaging app, and that means there should be messages on the messages endpoint, and for the admin user it should be as such. And yeah, so we have our flag over here and we are gonna submit this flag and we are gonna complete this room. I hope you enjoyed it, and you do give a like if you enjoyed it, and make sure to subscribe and drop down any comment if you didn't understand anything. And thanks for watching. We are just gonna complete this, and yeah, so thanks for watching.